Welcome to Elevated Excellence Elementary. In this session, we'll be taking electrolysis, part 2 of electrolysis. We've taken part 1, so I recommend you watch the part 1 of this topic before you watch this. So before you watch this video, so let's begin. We'll be taking the Faraday's laws of electrolysis, specifically the theoretical aspects. So what are the objectives of this session? The students must understand the concept of the laws of electrolysis. The students must understand the applications of the laws. The students must understand the applications of the laws and others. So, what is the Faraday's first law of electrolysis? It states that Faraday's first law of electrolysis states that the mass of an element discharged during an electrolysis is directly proportional to the quantity of electricity passed. Again, the mass of an element discharged during an electrolysis is directly proportional to the quantity of electricity passed. So we will notice that those key words are represented letters are represented by letters as they are written in the sentence. They are also represented by letters. So the mass m of an element discharged during an electrolysis is directly proportional to the quantity of electricity passed. So we need to understand this, though I guess we understand it later. So let's proceed to the second law before we begin. So okay, this is an illustration of the first law. So it states that the mass of an element discharged during an electrolysis, we will notice that it is the ions in the electrolytes that are discharged during electrolysis, based on what we were taught in the last video. So here, the mass of the element discharged is directly proportional to the quantity of electricity passed, which is Q. So for those that understand variation, we should be able to construct something like this. The unit of quantity of electricity Q is the coulomb. Yes, we should take note of that. The unit of this Q here is coulomb. So while the quantity of electricity has the formula to be current times time, this Q here has its formula to be current times time. So while the quantity of electricity is measured in coulomb, the current is measured in ampere and the time is measured in seconds. So and is measured in seconds, while Q is equal to I times T. Therefore, okay, maybe I should actually illustrate it here. So we have, if M is directly proportional, mass of the element discharged is directly proportional to the quantity of electricity passed. Okay, we have Q, which is equal to current times time. Therefore, we can say M is directly proportional to I and directly proportional to T. So here you can actually say M is equal to a constant. Okay, let's say Z I T. Exactly. So maybe I should erase this now. So okay, this should be, let's make this M is directly proportional to IT. Okay, so M is equal to Z I T. So we need to introduce this constant of proportionality. Here it is here. So okay, where Z is a constant, when M is expressed in grams, okay, the constant Z is the mass in gram of the substance liberated by the passage of 1 coulomb of electricity, that is a current of 1 ampere passed for 1 second, and is called the electrochemical equivalent of substance. So the constant here is called the electrochemical equivalent of the substance. So when we're writing the equation, it is mandatory upon us to introduce the constant. So now what does the second law say? It states that when the same quantity of electricity is passed two different electrolytes, the relative number of moles of the elements discharged are inversely proportional to the charges or the ions of each of the elements respectively. Let me take that again. It states that when the same quantity of electricity is passed through different electrolytes, so when the same quantity is passed through different electrolytes, the relative number of moles of the elements discharged are inversely proportional to the charges on the ions of each of the elements respectively. So now let's take, okay, we have here that John Faraday, his experiments showed that the minimum quantity of electricity required of a single charged ion is 96,500 coulombs. So based on this statement here, we have that when the same quantity of electricity is passed through different electrolytes, what do we have here? The relative number of moles discharged are inversely proportional to the charges on the ions. That is, okay, let's clear all this. It states the relative number of moles is inversely proportional to the what? The charges. We have that here, okay? So on the ions of each of the elements respectively. So his experiments now showed that the minimum quantity of electricity required of a single charged ion. What do we mean by a single charged ion? So an example is silver. An example is silver. So we have here silver. Based on the lesson we treated in the last class, we would learn that silver is among the electrochemical series, and it is positively charged, and it is a single charged ion here. So let's take silver as an example. His experiments showed that the minimum quantity of electricity required of a single charged ion is 96,500 coulombs. That is, the electricity required of this single charged ion is what? 96,500. Okay, let me write that out clearly. Here is what? 96,500 coulombs. Okay, that's the electricity, and you should know Q is measured in coulombs. Q is stated earlier. So 96,500 coulombs will liberate 1 mole of hydrogen ion. What does that mean? So hydrogen ion here is used here to represent the single charged ion. So it states that for any single charged ion, 1 mole of, let me write that down here, 1 mole of what the ion, 1 mole of that ion, yes. So 1 mole of the ion will liberate what? Will liberate, so 96,500 coulombs. So liberation here, when we are working with the calculation, it could also be equal to, so they are still the same. So 1 mole of this ion will liberate 96,500 coulombs. So what does that imply? It implies that this going, or okay, this should be, okay, what does that imply? It implies that when we have a double charged ion, for example, copper, so we have copper as Cu2+. When we have copper here, then definitely, what's wrong with the board? Please, okay, yeah. So then definitely, when 1 mole of ion liberates this 96,500 coulombs, then since this is 2 moles, then 2 mole of that ion of copper ion of that ion of copper ion is definitely going to liberate, you should guess what? It's definitely going to liberate 96,500 coulomb times 2. Okay, sorry. It's definitely going to liberate 96,500 coulombs times. It's definitely going to liberate this 96,500 times 2 coulombs. 96,500 times 2 is definitely 196,000 coulombs. You can punch your calculator. Oh, sorry, it should be 193,000 coulombs. So definitely, okay, let me raise this up. Okay, so 2 moles of ion is definitely going to liberate 96,500 times 2 coulombs. So we should note that. It's very important. So now, this quantity of electricity is called the Faraday. It's called the Faraday. This quantity of electricity is called the Faraday, and it is denoted by F, which implies that 1 Faraday is equal to 1 mole of electrons. This is different from the mole of the ions. Now, there was actually a break in transmission, so you might not notice it, but um, the reason I'm stating this is because I might have to repeat some things I've said earlier. So now let's proceed. So let's take the Faraday's second law of electrolysis again. His experiments showed that the minimum quantity of electricity required of a single charged ion is 96,500 coulombs. 96,500 coulombs will liberate 1 mole of hydrogen ion, and it has been explained here that a single charged ion requires liberates 96,500 coulombs. It liberates this. So in the calculation I worked out here, I stated that 1 mole of this ion, that this is it, 1 mole of the ion will liberate what? 96,500 coulombs. So for a double charged ion, for an ion that has more than a charge, so 2 moles of ion is definitely going to be what? 96,500 times 2 coulombs, which is 193,000 coulombs. So we should take note of that. So now it is now stated here that this quantity of electricity is called the Faraday, and it is denoted by F. So 1 Faraday is equal to 1 mole of electrons. Is equal to 1 mole of electrons. So the mole of electrons that is stated here is not the same as the mole of an ion. So take for example, when the copper ion is discharged during electrolysis, we have Cu2 plus it gains 2 electrons, then liberates what? The copper solid. So here, what do we have here? For here we have 1 mole of this here, which is the 1 mole of okay, I'm very sorry about, we have 1 mole of, okay, sorry, they're actually the same. So what I wanted to point out is that when it's stated that 1 mole of the element is not the same as what? Is not the same as 1 mole of electron. So they are not the same. These two statements are not the same. So we should take note of that. 1 mole of element is the one here, while the mole of electron is the what? So this content is the one here, but rather this contains 2 moles of electrons. 2 moles of electrons. So we should be able to identify that, which contains 2 ions. So that's what is stated here, that that 4 Faraday is equal to 1 mole of electrons. 1 mole of electrons is equal to 6.02 times 10 raised to power 23. This should be raised to power. I'm very sorry about this. So we should now let's take a look at the relationship between these um, between these quantities. So now what do we have here? We have that 1 mole of an element, which is something I just illustrated here, that 1 mole of an element is equal to 96,500 coulombs. So if you can remember, I stated that 1 mole of hydrogen ion is equal to 96,500 coulombs. So therefore 1 mole of what an element is equal to 96,500 coulombs, and 96,500 coulombs is equal to 1 Faraday, which is 6.02 times 10 raised to power 23 electrons. So we should remember this relationship, because what we have here is that 1 mole of hydrogen ion is equal to 96,500 coulombs, as it has been confirmed, and we also have that 1 mole of electrons, which is also the 1 mole of hydrogen ion, is equal to what 1 Faraday, and 1 Faraday is also equal to 96,500 coulombs. So when we begin working on the calculations, we get to be using these formulas. So now let's begin. During the electrolysis of its copper 2 salt solution, 0.4 mole of copper was deposited. What quantity of electricity was passed during this process? Let me take that again. During the electrolysis of copper to salt, 0.4 mole of copper was deposited. You should not forget, the ions are usually deposited when they are undergoing electrolysis. So what quantity of electricity was passed during this process? So now here it's stated that copper has a valency of 2. You should understand this. Copper has a valency of 2. So here you have the copper valency here. Can you see? So that is it. It has a valency of 2. So okay, so the equation for the deposition of copper is Cu, the copper 2 plus the copper ion plus the electron and the copper solid. So here it is, 0.4 mole of copper was deposited. What quantity of electricity was passed this process? So we need to construct the equation for deposition of copper, and here it is. The copper has a valency of 2. For you that watched the part 1 of electrolysis I made, you would find out that the copper here has 2 ions. It has 2 ions. It has a valency of 2 when we were treating the electrochemical series. So, and the copper here gains 2 electrons to form the copper solid. So I think it has been drawn out here. So it forms the copper solid. So now what do? We have 1 mole of the element here, 1 mole here. Okay, maybe perhaps I should erase this and draw that again. So we have the copper here. When we are given a question like that, we need to write out the equation for deposition. It's very important. So it gains 2e minus. The reason it is 2e is because of this. If it was silver, it would be an electron like this, 1 mole of the electron. So we need to note that. So now what we have here, to liberate the copper solid. That is it. So here it contains 1 mole. Here this contains 2 mole of electrons, while this contains 1 mole. So we need to understand that. So from the equation we have that 1 mole of the copper ion requires 2 mole of electrons, which is equal to 2 Faradays. So what we're trying to get is the quantity of electricity that was passed, and we should also know that quantity of electricity is also denoted in Faraday, because as it was stated here, as it is stated here, that this quantity of electricity is called the Faraday. It's called the Faraday. Okay, so now let's proceed. So we are trying to get that while comparing these formulas. So from the equation, 1 mole of copper ion requires 2 mole of electrons, which is equal to 2 Faradays. What does this sentence imply? What does it imply? It implies that 1 mole of copper ions requires 2 mole of electrons, and that's actually correct. 1 mole of this requires 2 moles of electrons, because here it is the 2 moles of electrons they are referring to. So 1 mole of the copper ion requires 2 moles of electrons. Okay, so let's put that down here. You have 1 mole. Okay, I think I have to expand this. 1 mole of copper ion requires what? 2 moles. Okay, sorry. Of electrons. So, and 2 moles of electrons is equivalent to 2 Faradays, based on what stated earlier. So 2 moles of electrons is equivalent to what? 2 Faradays, 2F. So now what do? We have that 1 mole of copper is equal to 2 Faradays. Then what? 1 mole of this of copper, 1 mole of copper is definitely equal to what? 2 Faradays. Can you see how this has been compared? So let me take the slide a little bit back so we can see how the Faraday is equal to the number of electrons. So here it is. It has been stated here that 1 mole. The experiments show that the minimum quantity of electricity required of a single charged ion is 96,500 coulombs. Therefore, 1 mole of hydrogen ion liberates this. Here as well, 1 mole of electrons gives 1 Faraday. So that's it. So now let's proceed with this. So when we have that 1 mole of copper gives 2 Faraday, so what do we need to do? Since it has been stated that 0.4 mole of copper was deposited, then definitely we can say then 0.4 mole of copper, then 0.4 mole we deposit X. So we can definitely get the number of farad that was liberated. So how do we solve a question like this? You should have understood this, but I'm going to take an explanation of that. So what do? We perform a step in mathematics that is known as cross multiplication. So we cross multiply. Oh, sorry, let me use color. We cross multiply this. No, I need to change it. So we cross multiply this here. So what we get? We have what? X times what? 1, which is equal to 2 times what? 0.4. So when this is solved, we have x is equal to, when we have 2.044, we know this is already 4 over 10, which is also 2 over 5. So 2 times 0.4 is definitely going to give us this 0.08. So there it is 0.08, which is 8 over 100, or 2 over 50, or 4 over 50 or rather. So definitely going to give us what? 0.08 Faraday. So we should know that. So we've actually gotten the quantity of electricity that was passed during this process. So that's our final answer. So now question 2. 0.1 Faraday of electricity was passed through a solution of copper 2 tetraoxosulfate 6. What maximum mass of copper is deposited on the cathode? What maximum mass of copper is deposited on the cathode? We realize we are still working with copper. So now let's take a look at that. As it has been stated earlier, the copper element has a valency of 2. So the equation for deposition of copper is this: the copper 2 plus the copper ion plus this, gaining 2 electrons and liberates the copper solid. So yeah, it contains 1 mole of it contains 1 mole, the 1 mole of the element. Yeah, it contains 2 moles of electrons here, and 1 mole of the element here. So from the equation, or from the question, what are we asked to solve? 0.51 Faraday of electricity was passed through a solution of copper 2006. What maximum mass of copper is deposited on the cathode? So we have to calculate the mass of copper that was deposited on the cathode. So how do we do that? So now, looking at this relationship here, we have that 2 moles of electrons is equal to 2 Faradays, as it has been stated earlier. 1 mole of electron is equal to 1 Faraday. So definitely 2 moles of electrons is equal to 2 Faradays, and 2 Faradays is equal to 1 mole of copper of this. So we should not get confused. This is referring to the electrons, while this is referring to the elements. Maybe I should write that down. So we have that what 2 moles 2 mole of electrons is equal to 2 Faradays, which is equal to what? So 2 mole of what? Of electrons here is equal to 2 Faradays. That's confirmed, which is equal to 1 mole of the copper 2 ion, which is equal to 1 mole of this. So 1 mole of this, which is also the 1 mole of the element, and 1 mole of the element in chemistry is equal to 63.5 grams of this of copper. So 1 mole of copper, so 2, and 1 mole of this is equal to 63.5 grams. That's a constant of copper. So 1 mole of that is equal to 63.5 grams of copper. So this is actually a constant number in chemistry. 1 mole of this is actually equal to this. So in some certain questions will be given, okay, here it is here. So copper is equal to 63.5, which is the mass of copper there. So now when we have that 2 mole of electrons is equal to 2 Faradays, which is equal to 1 mole of copper, and it requires 63.5 grams of copper. So we can actually compare these two here. So if 2 moles of electrons is equal to 2 Faradays, then 1 mole of copper is definitely equal to what? Okay, if 1 mole of copper, sorry, is equal to 2 Faradays, since 2 moles of electrons is equal to 2 Faradays, then okay, sorry, I think this quite confusing. Okay, let's solve that here. So we have 2 moles of electrons, which is equal to 2 Faradays, which is equal to this and this. So what we are going to do now is to obtain, okay, let's check this out. Okay, it's to okay, so it stated that what, if 1 mole of, so if you have 1 mole of what, copper here is equal to what, 2 Faradays. So is equal to 2 Faradays, then 0.4 mole of copper. I think this actually is, it's, oh, this is actually a mistake. Okay, we have that. So the error has actually been rectified. So let's proceed now. Based on a workout here, we have that if 2 moles of electrons is equal to 2 Faradays, which is equal to 1 mole of copper, then is equal to 60.5 grams of copper. So what do we do, since we're actually searching for the mass of copper deposited, and we have this relationship already here, and we have 0.5 0.1 Faraday of electricity already. So what can we do? We can say that if what 2 Faraday is equal to this 63.5 grams of copper, 63.5 grams of copper, then what happens? What do? We have the value here, 0.1 Faraday of electricity which was passed through the solution. Then 0.1 Faraday is definitely equal to x. So we can actually get the mass that was deposited when 0.1 Faraday was passed through it. So when we cross multiply and we work it out as I did earlier, so we are definitely getting this. So cross multiplying like this, then x times 2 will give what? 63.5 times 0.1. So we solve it, then get x is equal to 33.2 grams of copper. So definitely the mass that was deposited is 3.2. Final answer. So that's it. So now let's solve one more question. So calculate the mass of silver deposited when a current of 2.6 ampere is passed through a solution of a silver salt for 70 minutes. So we have these parameters here. So now how do we solve a question like this? So now we have that quantity of electricity used, okay, is current times time, as it has been stated earlier that Q is equal to current times time, which is the quantity of electricity that is measured in coulombs, is equal to the current times time. Okay, we have it already. So we have that here. Okay, we're actually going to get that first, because what we are searching for now is the mass of the silver deposited, and based on the parameters we have here, you using the steps I used earlier to solve this will be very difficult. So we have to change the step. So we're actually getting the quantity of electricity used first. So Q is equal to current times time, then Q is equal to, what's the value of the current here? 2.6 ampere here, okay, and the time 70 minutes. So as we all know, the SI unit of time is a second. So if you don't understand SI units, you can actually go back and watch my first video in physics, which is on dimensions. So let's proceed. So salt here is 70 minutes. So to convert that to second, we actually multiply it by 60. Multiply the 70 by 60 to get this. Then the quantity of electricity used is 10920 coulombs. So we've gotten that now. So now what are we going to do to get the mass of the silver deposited? So having written the equation for deposition, we have the silver ion here gaining an electron, then liberating this silver solid. So we have that here. Okay, maybe I should write that down. We have the silver ion gaining an electron, then liberating this. So here it contains 1 mole, like 1 mole of the silver ion. Here 1 mole of electron. Because of this, it contains 1. That's why here is 1, and here contains 1 mole of the solid. So now we have that. Okay, this has been written implicitly. So we have that Ag plus here contains 108 grams, and this contains 1 farad and 108 grams. So as it has been treated earlier. So okay, I think the explanation is here. Thus 96,500 coulombs is equal to 1 farad, liberated 108 grams of silver. Therefore, okay, so what has actually been written is that we have 1 mole of this, 1 mole of this, based on the relationship. Let me undo and get back to this relationship here. Okay, yes, I've actually got into the place. Let me allow me erase this and this here as well. Okay, so now based on this relationship here, we have to, okay, now this time around we no longer have 2 moles of the electron, we have 1 mole now. 1 mole of the electron, and 1 mole of electron is definitely going to liberate 1 Faraday. Then 1 mole of Ag, then gives, okay, are we working with the mass? Okay, of course you are working with mass, definitely giving this here, as it has been stated here, 108 grams of the mass, 108 grams. So we have this here. So now how do we work with this? So since we have that 1 mole of electron is equal to 1 Faraday, which is equal to 1 mole of argon, 1 mole of silver, which is equal to 108 grams. So we also have that 1 Faraday, oh sorry, I was wrong. Okay, we need to change this. So we also have that 1 Faraday is equal to 96,500 coulombs, is equal to this. Then we can now compare this, since 1 Faraday is equal to 96,500 coulombs and 1 Faraday here is also equal to 108 grams of silver. Then we can write this out. Then therefore we can extract this and say if 96,500 coulombs is equal to 108 grams, then based on our answer here, the quantity of electricity which is measured in charge, we have 10920 coulombs. We have then 10920 coulombs is equal to x, which is the mass of the elements we are searching. So how do we solve this? Let's punch the calculator. Let's punch the calculator. You can have it here already. So now, oh sorry, it's responding slowly. Okay, so we have this. How do we solve it? We multiply this together, which is 10920 multiplied by 108, you get this. So then it will be divided by this, then divided by what do we have here? 96,500 coulombs. So what do we get? We get this. Okay, let's confirm it here. 1222, 1,222 grams. So what do you have here? What do you have in the calculator? Okay, 12. Okay, yes. So it's actually very correct. That's 19 point, or is it 19? Sorry, okay, 12.22 grams. This should be a decimal point. So that's it. That's how we can solve it. So now let's move to, okay, let's solve the last question here. Okay, please wait. Okay, yeah, so we have to calculate the mass of copper deposited when a current of a 0.9 ampere is passed through a solution of a copper salt for 1 hour 20 minutes. Let me take that again. Calculate the mass of copper deposited when a current of a 0.9 ampere is passed through a solution of copper salt for 1 hour 20 minutes. The questions are very alike, they're actually the same. So how do we solve it? Okay, we are working with copper now, and we have that. Okay, I need to, let's clear this here. We have this here. When constructing the equation for deposition, we have the copper ion here gaining 2 electrons. Because of this, its valency is 2, then liberates was the copper solid. So we have here that it contains 1 mole of electrons, correct, and it contains 2 moles of electrons, 2 moles of electrons here. Then definitely is going to contain 2 Faraday, is equivalent to 2 Faradays of electricity, and 1 mole, yes, 1 mole of the copper correct, 1 mole of the copper, and this is actually not the value. Then maybe I should just undo to get to that of copper. Okay, let's undo, and yes, so now we have it here. So the copper contains 2 moles of electrons, 2 Faradays, 1 mole of this, and 60.5 grams of copper. Like I said earlier, this is actually a constant value. So what do we do now? So since we have this here, we can actually get the quantity of electricity by making use of the formula Q is equal to IT, which has been done here. When Q is equal to IT, then Q is equal to 0.9 times 80 times 60, which is equal to 4320 coulombs. We have Q here as okay, sorry, I need okay, we have Q here as 43 20 coulombs. We have 4320 coulombs here. So looking at this, we have that if 2 Faradays is equal to this, yes, if 2 Faradays is equal to this, and we also have that 1 Faraday, if 1 Faraday is equal to, okay, let me write that with this. Okay, we have that if 1 Faraday is equal to 96,500 coulombs. So we have 2 Faradays here, then definitely 2 Faraday is equal to 96,500 times 2 coulombs. So then if 2 Faradays is equal to this, if 2 Faradays is equal to this, then we can say that this itself, and we also have that 2 Faradays is equal to this here, is equal to 63.5 grams here. Then we can actually extract this away as we did earlier, then say the 96.50 times 2, okay, is equal to this. Then definitely, based on our answer here, the quantity of electricity passed 4320, so 4320 coulombs is definitely equal to X. So we can actually get the value of the mass of copper deposited. So now we need to punch our calculator. By saying, okay, 96,500 times 2 should give us 193,000. Okay, 193,000. Okay, that's actually correct. So now we can actually say 4320, the multiplication of this, times 63.5. What do we have here? So we can actually divide it by this 193,000. So what do we get? We get this. So which is what? So there is here is our answer. So what's the answer gotten here? 1.42. So 1.42, that's actually very correct. So we've actually solved about 4 questions. So now here is another question. So, and this question will not be solved by me, it's going to be solved by the winner definitely. So when you're able to get the correct answer, you send the mail to this, to any of this, you send the answer to any of this, then you get rewarded with your full explanation. So this is the question. So I'll recommend you watch the video all over again in order to understand it well. So thank you very much for watching. I really appreciate your time. Thank you very much.